What's going on, you guys? So today we're going to implement our own square root function. So obviously this is pretty simple if we can use library methods. So if we can import kotlin.math.pow, which is just power, we can just return x to double pow, raise it to the half power, and cast it to an int, and we can just return that. But we're probably, if we get asked this question, we're probably going to be asked to use it without any library methods. So let's think about how we can do that. Okay, so now let's do this without. Okay, so 4, its square root is 2. Square root of 4 is 2. Square root of 8, oops, sorry, is like 2.8 or something. And we're looking for, so we're returning an int. So even though this is 2.8, it's going to return just 2 because it lops off all the decimal values. Okay. Okay, so square root of x compared to x is always greater than the square root of x. Let's think about that. So what about for x less than, oh, for integer values, right? So like the square root of 1 over 2, we don't have to worry about that because x will always be an integer. Okay, so for integer values, all values greater than 0, x is going to be greater than the square root of x. So how do we get 2 here? So there's a bunch of candidates, right? The answer will be somewhere between 1. It will be greater than 1, and it will be less than x, less than or equal to x. Okay, so it will be somewhere in here. This is the solution space. And likewise for 8, it'll be in 5, 6, 7, 8. So we can do a binary search over the possible solution space to figure out which integer we're going to return. And how are we going to search over this space? Well, let's see. So 4 squared is 16. 16 is greater than x. So we want to move lower, right? And 1 squared is 1. 1 is less than 4, so we want to move higher. So yeah. So we'll move higher. So we'll have 2 pointers, right? We'll have a beginning and end. Well, let's do left, right. We'll have right and left, and we'll move right lower when right squared is greater than x. And we'll move left higher when right squared is less than x, less than or equal to x. So for example, let's say, where would we be at? Let's say, what's an example of that one? So if we do a binary search, we're going to have a midpoint. And our midpoint is going to be the midpoint of our array. So we're going to do, midpoint is going to be left plus right over 2. And let's do it for 4. So for 4, it's going to be 5 over 2. It's going to be 2. So mid, in this case, is going to be 2. So let's move. Let's move this stuff up here. Okay. Okay, in this case, midpoint's going to be 2. Midpoint squared equals 4. So what do we want to do? In this case, we'd want to return it, but let's think about like a general solution. So if midpoint squared is less than x, what do we want to do? Let's say it's greater than x. Midpoint squared is greater than x. Then that means if we know that all the values to the right of midpoint are going to be too big, then we can just search. We can search in the other half. So from left to, and we can set right equal to mid minus 1. Is that correct? Yeah, we'll set mid equal to, we'll set right equal to either mid or mid minus 1. I'm not sure, let me see. So if mid is too big, we'll look at the left side of our solution space. Otherwise, what will we do? Otherwise, we'll look at the right side. Yeah. So we're chopping the solution space in half on each turn. So if it's too big, we want to move the right. We want to look at the left lower values. If it's too small, we want to look at the right higher values. Else we'll set left equal to mid plus 1. Yeah, so either way, we're either looking at we take the midpoint and we're either going to look at the lower values or the higher values on the next turn. Okay, so what is that going to look like? So we're going to have some kind of a while loop, and we'll come back to the bounds on that. We're going to have a variable left. We'll start it at 1, variable right, and we'll set it to x. So our midpoint will equal left plus right divided by 2. And if mid times mid is greater than x, if it's too big, then we need to look at the left-hand side of our solution space. So we'll set right equal to mid or mid minus 1. Else, we'll set left equal to mid or mid plus 1. But mid might be the answer, right? For example, here mid 2 is the answer. So we don't want to skip mid. Okay. Let's think about this. And then we're going to either return left or right. So we have to figure out what's our stopping condition, and what's our return value. Are we going to turn left or right? Okay. So let's go through this again. Okay, so left, right. Okay. Mid equals, oops, x equals 4. Mid equals, in this case, 4 plus 1, 5 over 2, so 2. So mid squared is 4. Is that greater than x? No. So we're going to set left equal to mid. So this equals 2. Okay. What next? So now mid is left plus right. 6 divided by 3, so 3. So 3 squared is 9. Is that greater than x? Yes. So let's set right equal to mid. Okay. Now what? So mid is now 5 over 2, so 2. 4. Mid 4 is not greater than. Okay, so we want to stop when we get here. So we're going to stop when left is less than right minus 1. And in this case, we want to return left. Let's check that by running one more example. Let's do 8. Left, right. Okay, so midpoint here, left plus right over 2, so 9 divided by 2 is 4. Okay, 4. Okay, 16 is greater than 8, so we're going to set right equal to 4. Okay, and now let's see, mid is left plus right, so 5 over 2, so 2. 2 squared is 4, which is less than 8. So we set left equal to 4. Uh-oh. This is a problem. Because we've skipped 2, right? Because the square root of 8 is 2.8, but we're going to return 2. Yeah, so then in this case, when we set left equal to mid, we skip our answer. So this cannot be right. What if we just add 1? Okay, so let's think about it. So let's do 2 examples with just adding 1. So right is 4, left is 1, mid in this case is, oh wait, what? What happened here? Hold on. Wait, mid in this case is 2. 2 squared is 4. So set left equal to, oh, actually, you know what? I did this too soon. Let's see here, hold on. So let's set left equal to 2. Okay, now what? So mid is now 6 divided by 2 is 3. 9 is greater than 8, so we're going to set right equal to 3. Okay, and now what? Now left is 2 less than 2? No. So are we going to return left? Oh, okay. So does this work? I think this works. Cool. Okay. Let's check. Oh, and let's think about edge cases. So what happens if we give 0? Okay, so 0, it should just return 0. What if we give 1? So left is going to equal 1, right is going to equal 1, and it just immediately exits the for loop, and it returns 1. Okay, so if x equals 0, we'll return 0. Okay, let's see if this works. Oops. Let's comment this out. Oh, so we're having an integer overflow error here. So we need to update. So like if x is like the max integer value, left plus right will do an integer overflow. So we need to do a little optimization to try and avoid the integer overflow. So if we do this, if we do right minus left, these are equivalent, right? So if you for this first value, right? If we multiply by 2 and divide by 2, same value, right? So 2 left divided by 2 plus right minus left over 2. So we're getting the same base. So we do 2 left plus right minus left equals right plus left equals our original. So this equals our original. Left plus right over 2. Let's just do an example. Let's say 2 and 2. So 2 plus 2 on the right side, 2 plus 2 is 4 divided by 2 equals 2. On the right side, left, 2 plus 2 minus 2 divided by 2 is just 2. So yeah, these are equivalent, and it also avoids that integer overflow error. We could still potentially hit one. Let's think. If x is the max integer value, oh no, this will still work for the max integer value. And also this one. So mid could also be an integer overflow error. So we can just divide both sides by mid. And so that's using lower values. So that's giving us some headroom for the maximum integer values. Let's see. Okay. So we're using binary search in this case, and the runtime, so each time our search space gets cut in half, so that is O of log n time complexity. And we are storing 2 variables only, so this is just O of 1 space complexity. Storing 2 integer values. All right, you guys, so that has been square root of x. Stay tuned for the next one. See ya.